Today is the last day, day 9. So we have finished almost 8 days. This is 9th. Sorry, 10th day. Sorry, I forgot.
Last day of Gaian
Last day,
project.
10th day. Okay, we already finished 9 days. Okay, so today is the last day. Okay,
Of
let's.
Gaian course.
So today he
Investigate some modifications
yeah.
of GNN design and
Please go
some
ahead.
modifications of ZNN design. So today we will consider different modifications, some advanced model aimed to continuous time recurrent neural networks. We will have no time to consider all in details, but in any case, material which we will present today is advanced, and you will have material, and next time if you have, we'll see. You can use ideas presented in these modifications in your future paper if you need. First part will be aimed to one improvement, one modification of gradient neural network design. Then we will consider some modified ZNN designs. In third part, we will consider one combination of solving matrix equations and neural networks. And in last part, according to my plan, we will consider compute generalized inverses using symbolic tool available in package Mathematica. We will start from one improvement of GNN dynamics, gradient neural network dynamics, called gradient-based GNN dynamics. GNN, shortly. It was not easy to devise appropriate title for this kind of dynamical system because GNN is based on gradient descent optimization method. And say again gradient based was possible, unnecessary, but I didn't find something better. And shortly we will denote this new kind of dynamical system by GGNN. Such dynamical system can be applied in solving different matrix equations, vector equations. We decided to apply GGNN model in solving linear matrix equation AXB equals D. Of course, later it can be applied in solving Moore-Penrose inverse, solving Drazen inverse, matrix inverse. If we want to find matrix inverse, we will consider particular case in which we have what will be for B equal to, D will be equal to identity. Of course, later we can consider many different cases. If we want to compute Moore-Penrose inverse, instead A, we will consider A transpose or A transpose A. B will be identity matrix. D will be A transpose. error matrix in this case is AV of t b minus d or d minus. I think here is d minus. AV of t b. Then we need goal function defined as Frobenius norm of E of t. And after that we obtained GNN dynamic in form V dot, which is derivative of t of V of t with respect to t equals derivative of goal function n minus gamma. In this way we essentially applied the gradient descent method, negative gradient. Gamma was scaling parameter, gain parameter as large as possible. In expanded form, it is equal to minus gamma, and here will be one minus also. A transpose d minus A v of t b transpose. It is original GNN model. We call this model GNN of ABD. Generality is one advantage of this model. GNN of I leads to GNN model for computing matrix inverse. GNN of A transpose A transpose will produce left inverse of A GNN of I. Excellent. A transpose will give right inverse of A GNN of A power k plus 1 I A power k will lead to Drazy inverse if k is greater than or equal to index of matrix A. Where is Murpen-Ross? In arbitrary case, when we have singular, can I write here? Can you see? No. GNN arbitrary from here, A transpose A plus lambda I A transpose will give Morpeno's inverse of rank diffusion matrix. Rank diffusion matrix is matrix which rank is smaller than dimensions of matrix, than minimum of m and n dimensions of matrix. Then, according to requirements of numerical linear algebra, or linear algebra, well, better to say. Oh my God, I will have no. We know that AXB equal D is consistent if and only if A dagger D, B dagger B, yes, B dagger B is equal to D. It is a requirement from linear algebra. And general solution is given in the form V of t equal, limit, it is limit V of t when t tends to infinity V tilde of V0. V0 means result depends on initial state. A dagger, D, B dagger, it is Moore-Penrose solution, plus V of 0, initial state matrix, minus A dagger A, V of 0, B dagger. It was interesting result which says that final result is defined by initial state matrix. For arbitrary initial state matrix, this solution is least square solution. If we multiply V tilde by A from left and by B from right, we will obtain A dagger D, B dagger B, A V0 B, but here will be minus A V0 B. These two terms will be cancelled and result will be A dagger D, B dagger B. And in case if this expression A dagger D, B dagger B is equal to D, we will have solution. System will be solvable. If not, system is inconsistent. GNN design will be able to produce something, and it will be approximation of exact solution. Our goal in modifying GNN design was to avoid this assumption. And this modification is based on application of gradient descent method for nonlinear optimization. Here I put a very small part of our presentation aimed to nonlinear optimization. We wanted to minimize multivariate nonlinear in general case function with respect to n variables. And the gradient descent method is defined in the following way. New iterative value equals old iterative value minus stated definition of gradient. It is vector of partial derivatives of given objective function. Gk is value of gradient in fixed iterative point xk. And we know that gradient descent optimization methods force gradient to zero. In finally iterative steps, gradient in optimization methods, nonlinear optimization methods, should be near zero. According to the function for GNN dynamics. Idea was to use, which is defined as A transpose D minus A V of T B B transpose. If we use error function defined as gradient, we will force this error function to zero. Force gradient to zero. We know that if we are in point where gradient is zero, it is not always minimum point. I was thinking, is this approach good statistical analysis according to linear algebra? I found some good property will be identically 3 times equal. Our idea was to define GNN dynamics based. In this way, it was useful to define GNN dynamical system based on 5, which compares GNN with G. It is condition for solvability of G of t equals 0. We will not find conditions for solvability. We can try. V of t equals to A transpose D B transpose. Instead of A, we will use A transpose A instead of B transpose. And now, solvability condition, it is A, it is B, it is D, it is new D. Transpose A, dagger, D, B transpose, then B dagger, transpose dagger, B transpose is here, looks as Moore-Penrose inverse. B dagger, B, B, and now we can apply elementary properties equal to A dagger is equal to B dagger, transpose. A transpose D B transpose is equal to B transpose. B dagger B transpose is just so no conditions for applicability. Equation EG of T have no conditions for. We decided to proceed in defining it was possible to do. And are the same. We will obtain a result the same, and we have no condition-based GNN motion is defined in form minus 8 B transpose. Beginning using this error function from epsilon G correct is because we choose the error function D minus AVB. Frobenius square. A transpose A. Pose. Moved. GG NN dynamic delta epsilon outside of T B B transpose. It is EG of T where is integral that input of GNN model. And it was V dot, sometimes X dot. And definition of this, it is easy to linear. And after all, V dot integrals. W should the application of integrator, we will go to side of GGNN model. It is time interval, proposed time interval. We will display this state variable matrix V of T should be. Here is time scope, Frobenius norm of solution. It is PDF. Here is a 2 workspace block. It's theoretical solution. Theoretical solution is plus V0 plus. It was necessary to compare GNN and final confirmation. Our numerical investigation of many times we obtained better GNN. Red is GGNN from 2 to 4, which includes behavior in one smaller part, faster convergence, of course, later when time tends to infinity, both models converge to the error to 0. Here is a picture corresponding to linear activation. Down is a picture What can we expect? Graphs outside looks almost the same, but they are not same. What is expectable when we apply nonlinear activation function? We can expect faster convergence. Here convergence starts in 2.5. They are in 3.5. Similar behavior, but both the fair comparison assumes linear case in both models and nonlinear case in both models. It assumes. First picture assumes the activation function applied to both models. It was a result published in. Possible to define ZNN model using a new error function. Possible. Same error function for ZNN dynamical system. e.g. is error function used is in. It is minus gamma e.g. dot constant matrices. We spoke that GNN model should be applied to time invariant case, and I was surprised when not all of us answered correctly to quiz, to question varying matrix case. And here e.g. dot will use only. There is still in my mind's dilemma how to answer if someone asks question. What if so far performed numerical experiments always gave identical results with E of t and EG of t. Experience. I choose here only two pictures to in all cases, or in almost all cases, is faster than GNN model. It is our first GNN. Now we will go to some modifications of ZNN. So it will only to make one, how to say, will not be break. We only ask question about this part of presentation, then we will continue.
Yeah. If you have any questions?
No questions, not interesting.
No questions.
Okay. Uh-huh. Now we will continue with several modifications of junk neural network. This day will be aimed to many modifications. It can be aimed only to modifications of ZNN models, for example, and then we can explain in detail. So, then 14 practical, 12 theoretical.
Lectures. 12 hour tutorials. Practical.
14. 12 and.
No.
We'll see. There is also one explanation about high order ZNN and why ZNN model for solve equals I. This is defined as E dot of t minus gamma E of t 0 equals minus gamma. ZNN model for solving problem of matrix inversion in constant matrix case. It is in constant matrix case. Difference, forward difference rule, and discretize x dot of t as xk plus 1 minus xk by tau, and xk is defined as value of x in time t equal to k tau. Xk plus 1 will be value of x in time k plus 1 tau. Desirable is to use small sampling time for discretization. So if we divide two successive values in this discretization based on sampling time and divide by sampling time, we will obtain approximation of time derivative. Then discrete model. This model with time derivative is continuous time. Now we will obtain discrete model. A xk plus 1 equals minus gamma A xk minus I. X of t is considered as value of x in k tau time instance. Derivative is defined using two successive approximations in two successive time instances. Now we multiply by tau and obtain A x k plus 1 equals A x k minus beta, where beta is tau gamma. We spoke about such parameter. AXK minus I will switch from continuous time model to iterative rule according to your AX minus I existence of matrix inverse equals to all iterative value minus beta a minus 1. And now we will approximate a minus 1 by xk. Because our iterations go to a minus 1. Result is new iterative value equals old iterative value minus beta. A minus 1 is xk. A xk. One plus minus beta xk a xk. Using that we obtained such iterative method times by xk and you obtain how to say goes fine, starts quickly in to diverge. Cancel iterative process when you obtain. And it was our idea with Newton iterative method. People with, how to say, familiar with Newton iterative step. So, ZNN discretization result is scaled Newton iteration. Why not to exploit this and use high order iterative method and define ZNN dynamics? Equivalent to second order Newton iterative method, why not use ZNN dynamics? Most popular high order iterative method, scaled hyperpower iterative process, SHPI. Noun result, how to say, scaled Newton iteration for matrix inversion. Yes, it was a noun result, which made the discretization of junk neural network and obtained scaled Newton iteration. Here we analyzed this process from junk neural network to scaled. So our more general idea was from scaled hyperpower iterations for matrix. Also, there was another result from this, from junk neural network to scaled Newton iteration. Okay. Euler, if we use another kinds of methods. Time models, in our case, junk neural network. And we will analyze relation between improved junk neural. First, we analyzed relations between junk neural network and Chebyshev method. It is hyperpower method of order 3. Chebyshev method. For beginning, it was our idea too. to investigate relation between ZNN and high order iterative rules. For beginning, third order, because original ZNN is related with second order Newton method. Frequently here we denoted ZNN by ZNN M, which means ZNN based on Newton method, or NM, I'm not sure now, ZNN, NM, possible, ZNN Newton method. Chebyshev method, Chebyshev iterative method. Chebyshev iterative method. Third order. This method is defined using Vk plus 1 equals Vk, new iterative value, old iterative value, I will have no finally chunks. I plus first order residual error plus second order residual error square. If we use only first order residual error, it will be first order iterative method, Newton method. Here we used second term. What was the idea? I will use iterations of high order and go back to continuous time model. Because switch from continuous time by discretization resulted in a Newton method, second order. Here I will use third order for beginning later, high orders, and define corresponding ZNN dynamical system. After simplification, it will give 3i minus a vk 3i minus a vk. K goes from 0 to infinity. Here is our error function. Don't forget our well-known error function is defined as I minus a v of t. Idea was to define new error function, EC, C because of Chebyshev error function corresponding to Chebyshev method of t. I will put here only t. Identically equal by definition to E of t Of course, if we remove second term, we will obtain classical error function. Our idea was to consider What will be if we include powers of errors, as it is done in hyperpower iterative method? E of t is I minus a v of t, x of t, okay, plus a minus I minus a x of t square. Simplification gives 2I minus 3a x of t plus ax of t square. And then we applied ZNN dynamics. Expected ZNN dynamics is dot of EC, derivative of EC is equal to minus gamma, should be here. Okay, I suppose gamma will be EC of t. And then it is necessary to compute. What to save, I don't know. We need derivative of EC. You can see better. It is equal to constant term, derivative of constant term is 0, constant factor, then derivative of x of t, minus 3a x dot of t. What will be next? We have ix of t squared, ix. I is constant, so result will be only two terms. Ix dot of t, ix of t plus ix of t, ix dot of t. Looks not simple. And true Newton method will assume it is equal to minus gamma EC of t. This investigation was around 2016, 2017, but thinking from current point of view, it looks possible to develop a ZNN model according to this general rule. This model EC dot equals minus gamma EC is not considered so far. There is possibility to investigate such model. It will not be easy for implementation. Theoretical analysis will be changeable, how to say, challenging, will be really difficult, but in general it will be possible to do something. Problem not investigated so far. What we did, we simplified EC dot. Simplified EC dot with assumption that AX is approximately equal to I. Here is not dot. Equal to I. And our decision and investigated case was AC dot approximately equal to AX dot. We have 2 times. But here is -3. Minus AX dot of t. Again, we assumed and then continued minus AX dot of t is equal to minus gamma EC of t. We saved the right-hand side, and it was our new model. First, our attempt was IEEE. We received heavy reports. Was possible to answer, but Henley editor told, "Oh, you simplified left-hand side, not simplified right-hand side." Reject was final decision. And after that, we continued with this model and another, how to say, bad situation. We used wrong results and didn't obtain so good behavior of ZNN CM model. Results were better than we presented here and published this paper in Philomath. It's a pity how to say, okay, Philomath is in scientific list, but possible was better to publish in better journal aimed to neural networks. Here is our model, minus AX dot of t equals minus gamma. EC in expanded form is 2 identity matrix minus AX of t times 3 identity matrix minus IX of t. X0 is initial state matrix, ZNN CM model. Here is Simulink. Of course, relatively complicated because right-hand side includes one more term. After that, we worked on ZNN models based on hyperpower method of order 4 and even higher orders. All In all cases, we simplified dot of EC, derivative of EC, as minus AX dot. Again, it is probably it will be possible to continue with original ZNN model without such simplification, and try again in IEEE journal possible. Here is error function corresponding to hyperpower method of order P. Here we have P minus 1 terms where residual is. This result has been published in Neural Processing Letters. Always, I spoke about this. Right-hand side is simplified. Here is considered time-varying case. Time-varying case is considered here. Because of that, behind AX dot, we obtain also A dot X. And results were fine, how to say. Here is comparison between ZNN Newton method, time varying case, blue, slowest, then Chebyshev method, red color is aimed to third order ZNN method. Third order ZNN method. And yellow is aimed to fourth order ZNN method. We can see clear improvement in convergence, acceleration in convergence. Time interval here is very short. Still, there is no convergence here, is still short, slightly longer, and we can observe convergence started for yellow and for red. It is first modification of ZNN. This modification is based on using high order iterative rules. Because we observed a relationship between Newton method and how to say, discretized ZNN model. Open problem here is to use EC dot in complete form without simplifications, without, even in constant matrix case. I will very shortly present another improvement of ZNN, then we will go to questions and continue later. Here is one improvement of ZNN dynamics obtained using fuzzy logic system. Very good journal, IEEE Transactions of Fuzzy Systems, recently published. Main idea was here is to modify ZNN dynamics using one exponent here on exponent on gain parameter gamma. What is new in ZNN design here, one fuzzy parameter. This fuzzy parameter can be defined using sometime varying expressions, of course. Could you repeat, please? No. Fuzzy logic system, yes. Here we decided to apply fuzzy logic, this parameter, using fuzzy logic system with fuzzification. Then fuzzy logic rules, apply fuzzy logic rules, and defuzzification, if then rules inside the defuzzification and obtain result. Input in fuzzy logic rule, in fuzzy logic system was E of t, norm of E of t. Frobenius norm of E of t. Why Frobenius norm of E of t? We want to solve, to force E of t to 0. And it is good to trace behavior of E of t during time. And according to this behavior, use if-then rules. And after that, defuzzification to generate output. Ni. Output is used as exponent of gamma. There was possible to use another combinations. Not only gamma power ni, gamma plus ni, for example. Gamma ni was one choice, possible choice, but our numerical experience showed that gamma exponent ni is best choice. We obtain better results. We tried here, how to say, ask help of people, experts in fuzzy logic and in decision making. Dragisha helped us, Darian, in defining membership functions. There was necessary to define membership function. And according to membership function, we will obtain fuzzification. And then apply if-then rules, if E of t is smaller, not smaller. After that, the fuzzification will give ni. Okay, here I put only main idea how to define define improvement of ZNN dynamic. There are a lot of details about fuzzification. Fuzzification is defined using appropriate membership functions. We selected one of possible membership function, the fuzzification with another function. It is included in this paper. I think that this paper is open here. No? We can open this paper. 300 is number of this paper. I know it is rough number. Rough number. Here is. Here is our falsification. It is membership function defined in this way. P-shaped membership function used for falsification, and put norm of E of t inside fuzzy logic system. If then rules, then the falsification. What is still open here? Possible that our choice the falsification if then rules is not best. I'm not expert in fuzzy. I asked help of several colleagues, but I feel still that here is possible to do something better, or use neutrosification, 3 membership functions, and try with results. People working in fuzzy logic frequently told me it is true application of fuzzy logic system. What can be useful for your future research? Try if you have 1 parameter, 2 parameters in your representations. Possible choice is to include 1 more parameter by fuzzy logic system or something. So it will be good to ask questions about these 2 topics, GGNN. No, it is not GGNN. We finished with high order ZNN and fuzzy ZNN, FZNN. Safik, can I ask questions?
Yeah. If you have any questions, please.
We will continue until we can work when cannot work here.
If you have any questions, please. Any question on fuzzy parameter? This is new things, GNN,
Yes.
ZNN with fuzzy parameter.
With fuzzy parameter, published in good journal finally.
Yeah.
IEEE transactions of my systems. In that time, this journal was, in any case, very good journals.
So what kind of application in fuzzy? The GNN, ZNN. Application.
Here is application.
Fuzzy.
Here is application in defining 1 more parameter used as exponent. It is not only possible choice. Gamma plus ni was another choice. We tried with different choices. Finally, a lot of numerical experiments confirmed it was necessary to perform many comparisons and obtain some here is because ZNN is also convergent, and it is necessary to show that in beginning modification gives faster convergence. Shabam, how are you? You want?
Sir, so when we are moving from like the regular ZNN that we were doing so far, improvement that it gives, is it significant in terms of the convergence rate or the computation cost?
Yes, of course. More complicated EC than E, and computation in each time instant is, computation is more complex. It requires implementation is also more complex.
So although the implementation is more complex, the convergence rate is achieved faster.
Convergence is faster.
And the same thing happens with when we go from a lower order to a higher order ZNN as well.
I presented one for, I think, order 4 after that, continue. According to your comment, always computation is more and more complex, and continue with high order than 4 really is with no sense. It's true. Order 2, order 3, order 4. Always we obtain such faster convergence.
To gamma function based on the error properties.
Are in improved model.
So like
These are two possibilities how
larger error is significantly lower. Such that
parameter of T in high order ZNN dynamics also. And we will obtain similar improving gamma. From another side, improving ZNN design. One of possible error function on power T plus error function on opposite power. High order ZNN model can be considered as one considered plus E square plus E third. Then say high order, because then reviewers will not be again satisfied with simplification from left-hand side and complete form from right-hand side. Better is to gives error function plus square of error function plus third order and so on.
And the VPFT ZNN or so whatever I have experimented.
Apply gamma of T on ZNN and save gamma in ZNN, and depends on gamma of T, which we will use in VP ZNN, possible that we will obtain. It is not fair comparison. Fair comparison assumes the same. Fair comparison assumes the same variety. More questions?
Let's continue.
Continue until we can cannot. Only one comment. Shabam told about possibility to include zero blocks, 0 rows and 0 columns. In that way, it will be possible to consider high order ZNN dynamics in a rectangular case and more pronounced inverse. But it will require more time. In any case, take into account that it is possible. Here we will consider one another improvement of ZNN dynamics. We know that the original ZNN dynamical system is based on design, the derivative of error function. I will repeat because of you, if you can start to trace. Derivative of error function is equal to minus gamma error function. We force error function to 0. It is original ZNN dynamics. But if we have noise, in our case additive noise, sometimes original ZNN design will not show good behavior. Here error function is defined as A of t, V of t minus I, which is aimed to computation of matrix inverse, of course. New in this ZNN designed is such a term based on integral. Gamma here is our well-known design parameter, gain parameter. Zeta, of course, again, greater than 0 is new design parameter aimed to improve convergence. So our expectation was that this integral term will be able to solve problem with presence of noise, in this case, additive noise. Here is expanded version of integration excansed ZNN model. Original ZNN model is of the form derivative of error function is equal to minus gamma error function. In integration excansed ZNN model assumes derivative of error function is equal to minus gamma error function minus new parameter zeta integral of E of tau d tau from 0 to considered time t. Integration excansed ZNN noise tolerant assumes noise, additive noise, for example, in the end. E of tau d tau plus noise. If we consider error function defined as E of t equals A of t, x of t minus identity matrix, we will obtain the following integration excansed ZNN model. For A dot x plus A x dot, it is E dot is equal to minus t minus I minus integral term zeta integral from 0 to t E of t will include noise. We can consider such model. As always, of t in left-hand side, it is minus gamma minus integral term. T left and right I minus A of A dot of t it from it is tau, which gives in thermodynamical system. Problems with new partition. To general error function define is equal to g of t, a of t minus matrix A. A is rank R, order, rank S equal to R. Case S equal to 0 is F is regularization parameter, and definitely we use this error function in VP. What can we expect as a result? We can expect when time exponential convergence rate force error function to 0, and 2, this matrix is in -1 of when, and in that case we obtain the limit representation G inverses. Here is table about F and G appropriately. We will obtain matrix inverse, left inverse, right inverse, outer inverse with range and null space. We already analyzed these cases in our VP ZNN model, arraying parameter ZNN model, if you remember. Different choices of lambda. In our discussion, you were interested about regularization parameter lambda. Many times I spoke that lambda should be as small as possible. Here is one relatively big value for lambda, 0.9, and we can see that red dashed lines are not good approximation of solid blue lines, which means that lambda equal to 10 power minus 1 is not appropriate. Results were satisfactory. Finally, ask something better than this approximation is not necessary. Of course, we can choose smaller lambda. We will obtain errors with smaller errors, but it will not be visible here. Here is new bigger problem. Very interested problems.
Yeah, you can have after question.
And tea break.
Have any questions, please?
And tea break, because next lecture will require more time.
Yeah.
Will require more time.
No question?
Is it possible that ZN model can also handle the electron noise in electronic circuit also?
Could you repeat, Rahul?
Is it possible that
GNN
ZN model
model
can handle the electronic circuit noise also?
Yes, it is appropriate for hardware implementation, such Simulink models. I will go back until I find first Simulink implementation. If we have appropriate hardware for this and put, how to say, it is finally aimed to theoretical experimentation because before hardware implementation. In general, Simulink are defined according.
And sir, one more question related to the fuzzy But in fuzzy inference
Fuzzy.
system, you have used a
You are
pi-shaped
interested in
membership
fuzzy.
function. So, sir, is that any special reason for using the pi-shaped membership function?
This fuzzy,
Yes, yes. In your
Please, if you can
IEEE
speak
transaction
slower,
paper,
will
you
be.
have used a pi-shaped membership function in the fuzzy system.
We use one membership function.
Pi-shaped, yes, sir.
Expert in fuzzy logic
Okay,
systems
okay,
and
okay.
ask help of colleagues, but still I'm still feeling that this problem can be improved.
Okay, sir. Okay. Thank you, sir. Thank you.
And other membership functions for fuzzification and other functions for defuzzifications are possible.
Okay, is there any question? If no question, please give big thanks to.
Thank you.
Now we have this tea break.
How long tea break will be? The main idea is to based on two general steps. And next step is to multiply obtained solution. Method can be used to solve linear matrix equation. Here, gradient neural network, and another approach is based on symbolic computation. Solve particular linear matrix equation using appropriate gradient neural network model. And second part will be aimed to solving linear matrix equations symbolically in package Mathematica. And after that, it will be. And from my side, first result has been published in journal Complexity 2017. Here is theoretical result which gives corresponding algorithm. And this paper was nice combination of algebra were included in this paper from algebra. Such results can be considered. Such equations were considered. Theory results in our case results originally here we repetition should be familiar with outer inverse and in M order of X is equal to image of B with unknown image analysis satisfying Penrose equation 2 and with null space equal to null space outer inverse and now individual element in the described ranges such that matrix equation B use of A B is equals to nice RB for RB and B are equivalent. Direct equivalent. Here one includes set of 4 and 5 for B. BA, B1, AB is equal to B. Part of proof. Do this elegant proof. can see probably one was x equal to base unknown to u of appropriate time b. And create matrices xw well-known equation xab equals bu. It is bu matrix equation buab equals 2 implies balance of one inclusion is will be from this space will be is a UAB, of course. Here is one inclusion, here is opposite inclusion, and second part says that is defined as and the set of, how to say, inner. It can be represented in form BU and applicable in computations. Here is one interesting representation of out even better and more practical result of AB, particular in obtained as solution of matrix equation with range and BUAB equals B. Visible here also. This outer inverse, we will have matrix must be satisfied. If this condition is not satisfied, this theorem is not valid. BU, AB will not be solvable because B, AB1, AB will not about general linear matrix equation with respect to B form. So requirement about equality BU, AB, if we consider BU here as X again, we will obtain X outer inverse X with prescribed range. Okay, BU, AB equals B should be solvable. B equals B with respect to B. And then multiply by B from left, we will obtain outer inverse, different outer inverse. U. The representation presented in B to generate class of, in first step, we need to solve, multiply U by B and generalized inverses. Approach left or right and to obtain final. In 96, we defined algorithm image. Verify first if rank of AB is equal to rank of B. If this condition is satisfied, then solve the matrix equation. BU-A can be used arbitrary method. Here, in this paper, from complexity, we choose GNN model, gradient neural network model, to solve linear matrix equation BU-AB equals B. And then one element from class of outer inverses with prescribed range. Here is description in 97 how to define GNN model, for solving linear matrix equation BUAB equals B. I several times mentioned this model for solving general linear matrix equation AXB equals D. In our particular case, we want to solve BUAB equals B. Condition for solvability is B, A, B1, A, B equals B. This condition is satisfied if rank of A, B is equal to rank of B. Because of that, in our algorithm, we verified first this condition. So if this condition, rank of A, B equals rank of B is satisfied, we continue and define, we will define GNN for solving this matrix equation. E of t is, of course, defined as Shaban. B minus. Okay. Can be from one side, from another. Only replace unknown matrix U by time varying matrix V of t. And in that way, we will obtain continuous time model, depending on time. And always is possible to find a relation between discrete time models, discrete time iterations, and continuous time model. Goal function is square of Frobenius norm. Gradient of error function is, minus will be here, I suppose. Where is gamma here? Question for professor, where is gamma here? Will be. B is in front of V of t. B minus B, V of t, A, B, and then A, B transpose. And finally, GNN model is relation between time derivative of V of t and minus gamma. And one minus here, sorry. It will be gamma B transpose B minus B V of t AB AB transpose. One gamma here. I think I can do this immediately. Gamma. Gamma. Here is gamma. Best way we can immediately make correct mistakes. Result of this GNN design, continuous time, recurrent neural network design, will be matrix V of t satisfying B V of t A B equals B, of course, because GNN design force error function to 0 when time tends to infinity, and when time tends to 0, this equation will be satisfied. If we multiply by a from L10, I will use time font to define this. AB, V of t, AB equals AB, which means that V of t is element of AB1. Matrix equation will give inner inverse. One solution is one inner inverse, another solution is another inner inverse, but always B, AB1 given a, here is V tilde V, which means V of t after infinite time period. V of t is a result obtained from GNN. Sometimes we put here V0. It is from outer inverses with range R of B, and we don't know about represented this GNN model. In this simulation, it is equivalent. Here is integrator. Here is gamma B transpose, element-wise type derivative. And we need integrator to solve system of ordinary differential equations. We, in last time instant, when matrix B from left and obtained corresponding outer inverse. Interesting combination, interesting Professor Bass. Matrix theory and interesting mention here, matrix equation is not consistent, and GNN model case. It is good property of. What is another good property here? For Murpen-Rose, alpha, J. J is arbitrary matrix. In initial state, we will obtain different solutions. Solutions V of t, which always will give in product B, A, B1. We are able to generate different inverses with prescribed range. Dual result defines, I will only analyze it. Here is not BUC. Here is CA, not identical, 3 equivalent with for arbitrary. 4 equivalent conditions is defined as C and CA and mal AV. I hope it is clear. VA equals CA equal to it and obtained from right inverse VC with prescribed null space of this rank if this condition is in continuation using appropriate. Here CAV equals linear matrix we use, don't know. Of course, there is this right range and will be to exist CAB path, system CAB path immediately matrix equations must be assumption rank of then B arbitrary B arbitrary BUC BUC BUCAB equals inner inverse C BUCAB equals inner inverse of CAB. This equation by C means that U is inner inverse of CAB. AB from right we will of CAB. AB from right we will see that U is again inner inverse to solve only one of these two equations. You can solve both equations to verify. It is necessary first to verify rank equalities between equations are not satisfied. This algorithm is not a it is enough to solve first of two considered equations in theorem. And return result in form BUC. It is another question. We will have material, one lecture more surely will be.
General model in real life application also like diagnosis of tumor, diagnosis of some diseases like can we use
It is
this?
in live, so
Fish
I
model.
was asking, can we use this model in real life applications like diagnosis of diseases, tumors and
Doing matrix equations, of
Yeah,
course,
yeah,
we
yeah.
can. It will, it will require corresponding these models. People who can work with this model and people from experts in medicine.
Yeah.
Patients, of course, it can be solved.
Okay.
Even if these matrix equations are solvable.
Interesting, sir.
Applications
Yeah,
are
very interesting.
in economy.
Thank you, sir. Thank you.
Applications are
Yeah, very interesting.
in economy.
Thank you, sir. Thank you.
Thank you.
if no, please give thanks to us.
Okay.
So after this, there would be a half an hour tutorials, some question of some problems.
So I can
Okay,
plan
after that
lunch.
we'll have lunch. After lunch will be one lecture. Okay. So this is the last lecture. Okay. So now what you'll talk?
Something symbolic,
Yeah.
solving equations in our Urquhart representation of general outer inverse C. B and C take care about dimensions. We will suppose that. Then what theory says about the inner inverse of X belongs to set of inner of C X defined if rank of this notation from previous lecture. Set of equals X and belongs to set of outer inverses with unknown rank of x not element equals, because now outer with range R of B, null space R of CAB is equal to, and as always, when we consider outer inverses, if we assign 1, 2 inverses, so-called reflexive inner inverses. Inverse with predefined range and null space, inequalities are satisfied, equal to rank of C, and finally all these ranks are equal in hands of ranks of matrices. A type of G inverse obtained in this representation depends on particular cases. First case for this, if you remember, forgot probably too many. Which matrix is strongly related with Moore-Penrose? Star. Inverse. A power k plus 1. Best choice is just index of A, y to be bigger than index of A. Result will be the same, but simplest computation is made with, if index is equal to 1, A power 3, 1 inverse arbitrary, used Moore-Penrose inverse instead of arbitrary 1 inverse, because Moore-Penrose inverse is most popular. Mathematica includes Moore-Penrose inverse frequently. If we have outer space of C, it will be represented in form B. There is one condition. Here you can space exist under this. Here must be assumed rank equals rank of datation will be used. But if we have, in this way, we can compute arbitrary outer inverse with prescribed range null space. I suppose you'll combine again sum of noun, but probably they will be included here, and if they are included here, formula well-known Urquhart representation. Computationally effective procedure for computing. According to this intention, we derived first some theorem 2, and it is related with part rank of C, or rank of B, sorry. And B arbitrary inner inverse of CA, there is one representative theoretical equivalent conditions. First condition says, in the form not possible to verify all these results, and these the results are related. It is notation for one particular outer inverse with dimensions which consider this equation. We will obtain CAB U CAB equals CAB. Just we want to find inner inverse of CAB. Left by CA, we need to assume condition. Also, theoretical analysis shows that BU-CAB equals B is solvable if and only if this equation is satisfied. Equivalence between 5 and 3 is well known in linear algebra theory. And if we replace BUC by related with outer inverses with AB inverses. And in part B, we obtained a representation was a generator of appropriate algorithm for computations. One is of the form BUC, such this matrix equation. These results are not representation of linear matrix equation. B is one inverse and which defines is with image R of B. Again, this rank constraint is always assumed in terms of inner inverses. Can be obtained as solution, and the result is equal to BUC. To define outer inverses with prescribed in form, B is related with BAB. Here in all cases we work, in all cases we will work of CAB, and matrix equation depends on rank equalities. If rank of AB, CAB equals B. Then solution U multiple. Here is dual result. To find outer inverses with prescribed null space. Corresponding matrix equation, we will obtain CABV, CAB. Consistent if and only if this equation is rank equalities between of this. We'll give a practical algorithm. Linear matrix B from left and in outer inverses with null space and inner not identical. All is in here B. We can consider B is equal to rank of C. And the result we defined both range and null space is obtained as rank equalities. This notation rho, see, this notation is practical, save space, but because rank of CAB equals rank of B equals rank of C will be required. Here is solution arbitrary of these two ranks of C and use solution our unique out. Here solve symbolically if rank of CAB is dual matrix equations. One of these two equations solve according to as BUC. Value of B or rank of CAB is less than this algorithm is not applicable. Finds we expect CAB, CA as C, it implies BUC will end condition rank of CAB for Urquhart formula. Immediately give output because of CAB. The equation is UC from right. We will see that U equal because rank of C. Again, or we will say inverse. Under constraint part 3 space. because x is equal to 1 as corollary because that solution of CAB possible only is given in parabolically. It to be original is called G, A, B, and C matrices score. Otherwise, it mathematically is proven because of each time if rank made of 1. Mathematica returns result an approach B returns result an approach B seems it can be done is I and to L to L of this function will be L with symbols. You need to find we'll use address and row vector in one row vector and solve corresponding equation then solve and then where was necessary to form this form is and from this matrix U and return nice numerical non-numerical sorry presented here A matrix 1. This choice B equals C equal 1 leads to equation B use A. Mathematica how small and from right needs to define function shift and I will find definition of A for in any case possible that some previous definitions will be included here. Find x equal to. Here is a result of subscript U ij. It all starts from matrix U with arbitrary elements, list of variables with flattened function. Result obtained using function solve is of the following form. Necessary to cut right hand sides of answer and put in matrix. Here and after all we multiplied U by A from left by A from right and obtain final result. It is group inverse. Possible, how to say, generalized inverses. There are many possible generalized inverses which can be considered. Another example is related with B equals to C equals A transpose, and this approach leads to computation of Moore-Penrose inverse. Penrose inverse, nice examples in symbolic form. On hands, never. And another example with arbitrary B and C matrices. The result will be outer inverse with prescribed both range and null space because of this matrices are of the same rank. And here is new title, tensor case. For Bangalore, tensor case. It is all.
If you have any question, please.
Without questions, we will not finish.
They have understood everything.
What?
Understood everything. No questions. Yes?
So better ask questions.
So maybe after some time we'll start on. Your wife will be coming?
I will see what is call again.
Okay. So you are overwritten here.
You all to the now at the concluding chapter of this beautiful journey.
About building connections, perspective, and ideas. Each day added a new dimension to our understanding, and we are grateful for the wisdom and experience shared with us.
Have been a backbone of the entire program.
Now, I would like to invite Professor Safiq Ahmed. Sir, please.
Thank you very much for inviting me. This is to thanks our speaker, Professor Predrag, a long travel from Serbia to India. Again, thank you so much for your lectures you have given, along with 6 different and its application to be helpful to our think. They have two more professors were conditioning problems, and also Professor Atikant Behra from IIC Bangalore. He all these lectures from the numerical linear algebra basically since when problem is ill condition, if it is well condition. Okay. Given thanks all our successful printing mementos and preparing posters and office staffs, Jitendra Burma and Murphy, who have like food and also this transport arrangements. All these things they have done successfully. Okay. So after that, I would like to thanks our Gyan coordinator, local Gyan coordinator, Professor Coordinator Gyan from Hyderabad. This entire money to hold this Gyan program, and also given all this freedom to conduct this course. Without you, we could not hold this program. I think our students, if they want to work with you also, they can work. And to thanks to came over the different part of the their feedbacks also. If they have problem, we'll be keeping all this. Anything if you require in future, so Predrag would be.
Thank you, sir.
Grateful thanks, guidance, your clearing teaching.
Now, I would like to invite Professor Predrag. Sir, please come to stage and say.
I expect to say something put in this difficult. It is full of to all organizers here currently. Special thanks to Visa about traveling, about our program. Thanks for how to say thanks for such a not so easy topic as it is recurrent neural network and but we tried our life and in future results and publish your
To the HOD of the department for their support and the providing our department, Dr. Sanjeev Singh. Sir, please come to stage.
Okay, so after 10 days, I think organizing this course, and the topic is very interesting. I think if you are from related area analysis, these techniques can be used there also. You have make proper notes and all those things so that you can use it. You enjoy the campus also. So thank you for coming for this program. Okay.
You, sir, coordinators and participants, and the organizing team for making this Gyan course a memorable experience. Let's give a round of applause to everyone who made this possible.
To express our heartfelt appreciation. Now I would like to thank you, sir.
Now I would like to invite Professor Safiq Ahmed to felicitate HOD, sir.
Now our technician and technical Ravinder Rana. Now I would like to invite Safiq Ahmed sir to felicitate. And continuous support throughout the course. Pinky Didi, me, Pravakar Barik and Sanket Lam. Didi.
Will present the certificate to all our respected participants. Please come one by one. HOD sir and Pedrak sir, please come.
Next, Pinky Didi. Next, Dr. Rahul.
Sir,
Next, Himanshu Yadav. Thank you, HOD sir. Now, Safiq sir. Gautam Chaudhary. आशुतोष कुमार, नेक्स्ट भाग्यलक्ष्मी, धीरज कुमार गुप्ता, नेक्स्ट शैलेंद्र प्रधान, नेक्स्ट शुभम, नेक्स्ट एमडी आबिस रहमान, नेक्स्ट ललित का, नेक्स्ट माही राठौर, नेक्स्ट देवाशीष,
मेल कर देंगे सर सब। ओके
यस ए बी,
नाम बोलो मैं
गौतम चौधरी,
10
सिद्धि जैन,
8
श्रीवास्तव,
9
ललित कार्तिक,
8
आशुतोष कुमार,
9
एमडी आबिस रहमान,
9
देवाशीष,
9
डॉक्टर राहुल,
10
शैलेंद्र प्रधान,
9
संकेत,
10
करनाज काजी,
5
डॉक्टर पिंकी खातून,
10
एबिच,
6
प्रभाकर,
10
धीरज कुमार गुप्ता,
9 on your mail, please check your mail proper.
वो अभी सर रेडी नहीं हो पा रही। The final vote of thanks.
With all this, thank you very much, Andage, and also thanks to our volunteers, our operators, our office staff, department HO this event. Wish you all the best. Thank you so much. Participants also very attractive, and they were present all the 10 days. After this, there is a refreshment, and tea, coffee is there.
Sir, with that we officially conclude the closing ceremony of the